All right, so this is the second day of probability notes that we've covered during our AP review. So this section is primarily about discrete random variables and how to calculate things like expected value and the mean and the standard deviation. Okay, so in discrete random variables, we call the mean the expected value because it's what we should expect to happen. So for example, if you look at this data table, a store owner tracks the number of customers that enter his store at the first hour and figures out the following discrete random variable tables. So if we wanted to find the expected value for the number of customers for this store owner, we would do the probability of getting 0 customers times 0 customers, and the probability of getting 1 customers times 1 customer, and we would add that, all 4 of those values, and that would give me 1.2. So we would expect about 1.2 customers in the first hour. Now the standard deviation of the distribution, we often call this the Pythagorean theorem of statistics. So we do the value you got, so 0 customers, minus the expected squared times the probability of getting that. And then we calculate all of those and then take the square root, and that gives us the standard deviation. Okay, so that's the first thing we're going to touch on. The next thing is a situation is binomial if it follows the set of conditions below. The number of trials are fixed. Each trial needs to be independent. There can only be 2 outcomes. That's where the bi comes from. And the probability of success remains constant. So you have to check all of those conditions before running a binomial anything. So if you're reading a word problem and it says something like, what is the probability that blank out of blank, that should trigger you to check for those binomial conditions. So all probabilities of the outcomes should add to 100%, right? So if you're finding the complement, so say it says what is the probability that he has more than 0 customers, you could do 1 minus 0.2, and that would give you the probability of having it more than 1 customer. Okay, so let's kind of see how the College Board presents this on their formula chart. So the probabilities are given like this on the formula chart. This gray box is here because those are the probabilities we covered yesterday. So here, the probabilities that we're going to be looking at today are the expected value and the variance. Now, keep in mind that the variance is related to the standard deviation because the variance is the standard deviation squared. So while it doesn't often ask you for the variance, we can just find the standard deviation of x by taking the square root of the variance of x. And notice it tells you that in the formula, you just have to know that you need to take the square root. And then these are our probability formulas for binomial distributions. Now, some additional rules that are really important that they're not on the formula chart, which is you just have to know them. If you multiply a number times a distribution, like say you want to look at profit and you're charging $10 for every t-shirt or something like that, you would just multiply that number times the expected value. If you're going to add something, say in the situation of a curve, and I add 10 points to everyone's scores, I would just simply add the value of 10 to the expected value, and that would shift over my mean. Now, what doesn't change when you're adding a value is the variance or the standard deviation, right? Measures of spread when you add something don't change because you just simply moved the data over. Whereas if you multiply the data by, say I multiplied all of your test scores by 2, right? That'd be very extreme, but if I multiplied all your test scores by 2, that would change the spread of my data, and I would need to square that multiplier by the variance. Okay. Now, let's look at an example. The first thing I want to talk about is how to effectively use your calculator on examples like this. So, to save time, you're going to want to use your calculator for probability distributions. So, you're going to want to enter your probability distribution in a list So you put your values in one list and your probabilities in the other, and then you're going to use one variable statistics to find the expected value in the standard deviation. So let's kind of see what that looks like, and then we'll come back to this binomial situation. So you played a sorry, y'all. You played a game with your friend in which the scores range from 0 to 10. After you play the game several times, your final scores are recorded. So here's the distribution. We want to find our expected score. So I'm going to label my score S. And then I also want to find my standard deviation of my score. Now, in order to find the expected score here, I would do 6 times 0.4 plus, and then I would do 7 times 0.3. However, you don't have to show all that math for the College Board. You can put some dots in the middle and then do 9 times 0.1. And then we're going to leverage our calculator to solve this. And the same goes for the standard deviation. You don't have to show that calculation. We can do that heavy lifting in the calculator. Okay, so what I'm going to do here is I am going to open a new document, and that wasn't what I wanted. I'm going to open a new document, and I want to add a listen spreadsheets. So I just labeled my score as S, so I'm going to label that column S, and then I want a probability column to put in my probabilities. So my score distribution looks like this. I have 6, 7, 8, and 9. My probability of getting a 6 was 40%. My probability of getting a 7 was 30%. My probability of getting an 8 was 20%. And my probability of getting a 9 was 10%. Okay, so now what we're going to do is we're going to add a page and just add a calculator document. So add a page and then just add a calculator. So from the calculator screen, you're going to go to Menu, and then we're in Statistics, and then we want to run a stat calculation, and we want to do one variable statistics. And we only have one list here. So the X list is the scores, and then the frequency list, this is what's a little bit different about sometimes when we run this. We're going to put probability, and then that's going to spit out all of the values we're interested in. So if you look here, our X bar or our mean, in this type of probability problem, that's the same thing as our expected value, so it's going to be 7. And then our standard deviation here is 1. So I'm going to switch back to my page. So my expected value here is 7, and my standard deviation is 1. Okay. So that answers that question, and it goes over how to do the thing on the calculator. So now you win a game if you get a score of 8 or higher. So we want to find the probability that you win a game, right? What is the probability that you win a game? Now, you win a score if you win a game if your score is 8 or higher. So we want to focus on those two probabilities. So if you look here in this table, the probability of getting an 8 is 20%. And the probability of getting a 9 is 10%. So my overall probability of winning is 30%. Okay. Now, the next question, we're going to go back to those calculator skills that we were talking about, right? So you play a game 5 times in a row. We want to know what is the probability that you win a game at most 2 of the 5 games. Okay. So what is the probability that you win at most? That's a good indicator that I should kind of go through the motions of checking to see if it's a binomial. So each of these trials, so let's go back to those just to kind of remind us. So I want to check for there's a fixed number of trials. Yes, here there are 5 trials, that is fixed. Each trial is considered independent. If you won, the first game doesn't impact your ability to win the next game, so yes, we would consider that as independent. There are only 2 outcomes. You either win or you lose. And then the probability of the success remains constant. We just found the probability of your ability to win, so that means that our probability of a success remains constant. So here, what we're going to do is we have 5 trials. The probability of winning for you is 30%. And then we assumed that each game was independent. Okay, so that means we can do a binomial. Now, we want to do this in our calculator. What is the probability that you win at most 2? So that means you can win 0, you can win 1, or you can win 2. Now, if we were going to leverage the formula, let's go back to the formulas. Look at the formula for this. N, choose K, times the probability of a success to the power of K times 1 minus the probability of a success to the N minus K. Now, we could do that. So if I was going to do that in this example, that would look something like 5. Oop. I don't know what happened there. That would look like 5, choose 0, 0.3 to the 0 power, and then 0.7 to the 5 power. And then we would need to do that 3 different times here. Now, we can actually do this in the calculator, so I'm going to show you how and remind you how to do that. So, if we would like to do a range of numbers, use a binomial PDF if you want one specific binomial outcome, and a binomial CDF if you want to compute a probability of an interval. So let's go back to our Inspire. So I don't need to open a new document in this situation. So I'm just going to do menu. I'm going to do statistics, and then I don't want that. So menu, statistics, and then I would like to use a distribution. Now, remember, binomial PDF is if you have one single value. CDF is if you have a range. So I'm going to pick the CDF. The number of trials is 5 here. The probability of success was 30%. My lower bound is 0, and in this situation, my upper bound is 2. This will depend on your problem, so you need to make sure you're reading it accordingly. And then I'm going to hit enter, and it will spit out an answer for me. So the probability of this event happening is 84%. So let's go ahead and write that. So the probability that your score is at most 2, so less than or equal to 2, is 0.84. So that's just a quick refresher on how to use the calculator appropriately. So let's kind of look at a model and see how we can use this in a problem. After winning the national championship, a local sports team is selling t-shirts. Each customer may purchase up to 4 adult-sized shirts and 5 children's shirts. Let A be the number of shirts purchased by a single customer. The probability distribution for the number of adult shirts is given below. Okay, so we want to compute the mean and the standard deviation. So mean means that we would like the expected value of adult shirts. So here we would do 0 times 10% plus, and then we're going to put some dots and leverage our calculator. And then our standard deviation, we're pretty much going to rely on our calculator for this one. You can do it by hand, but it's much easier to let the calculator do the lifting for you. So here I'm going to go back to my calculator and I'm going to put this distribution into a list and spreadsheet. So I'm going to open a new document, add a list and spreadsheet. Now here they already defined the variable as A, so I'm also going to define it as A, and then I also want that probability column. So you can have 0 shirts, you can have 1 shirt, 2, 3, 4. Now the probabilities are as follows. So I have 10%, 15%, 55%, 5%, and 15%. All right, so once I have that, I'm going to go to my calculator screen, so add a page and add a calculator, and then do menu, statistics, and then I would like to just run a stat calculation, a 1 variable statistic. I have 1 list. Now my X list here I labeled as A, and then my frequency list I labeled as probability. And I hit enter. So I can see that my expected value here is 2 shirts, and my standard deviation, if I look, is 1.09, which I'm going to call 1.1. So let's go back to our document. So my expected value was 2 in this situation, and then my standard deviation is 1.10. Suppose the mean and the standard deviation for the number of child shirts purchased by a single customer are 2 and 1.5 respectively. So I'm actually going to write that out. The expected value for a child shirt is 2, and the standard deviation for a child is 1.5. Okay. We want to compute the mean and the standard deviation of the total numbers of adult shirts purchased by and children's shirts purchased by a single customer. So here, we're essentially finding a combined curve. So we want the expected value of the total shirts. So my expected value for A was 2 shirts, and my expected value for children was 2 shirts. So my total expected value gives me 4 shirts. Now, the standard deviation, we're going to have to use that Pythagorean theorems thing. So we're going to do the standard deviation of the total is equal to the square root of 1.10 squared plus 1.5 squared. You type that into your calculator and do 1.86. Okay. Now, that would be fine and dandy, but ultimately you're probably selling shirts to make money, so we're gonna figure out how much money we can make. So suppose each child's shirt costs $12 and each adult shirt costs $24. We want to compute the standard deviation of the total amount spent per purchase. So if we're calculating this expected value of like the amount spent, the money, we're going to do $24 times the 2 expected shirts for the adults plus the $12 times the 2 expected shirts for the children. And when I calculate that, it's $72. And then for my standard deviation of the cost of the shirts, here I'm going to do the square root of 24 times 1.10 squared, and then the same thing, $12 times 1.15 squared, right? Because remember, multiplying something changes the center and the spread of the data. So here, that value for the standard deviation would be 31.95 cents. There's $31.95. Okay, so that completes that example. So we have one more example I want to go through, and this one is actually a Release College Board question. So let's look at it. So it says at an archaeological site, there was an ancient swamp. The bones from 20 brontosaur skeletons have been unearthed. The bones do not show any sign of disease or malformation. It is thought that these animals wandered into a deep area of a swamp and then became trapped in the bottom. The 20 left femur bones were located, and 4 of these left femurs are randomly selected without replacement for DNA testing to determine gender. Okay. So the first question it asks us, let X be the number out of 4 selected left femurs that are from males. Based on how these bones are sampled, explain why the probability is not binomial. Now, if you only have 20 bones, then that's not a large enough sample size for taking out 4 bones without replacement for there to still be independence. So here, since bones are sampled without replacement, the selection is not independent. Okay. Now, suppose that the group of 20 brontosaurs whose remains are found in the swamp were made up of 10 males and 10 females. What is the probability that all 4 in the sample are male? Now remember, you're pulling a bone out and you're not replacing it. So the probability the first time of picking a male is 10 out of 20. Now, we want the probability of picking 4 male bones in a row. So you already picked one of the males, so that would be 9 out of 19 for the second probability. Now you've taken 2 of the male femurs out. So this third probability would be 8 over 18, and then that fourth probability would be 7 over 17. Then I would multiply those out of my calculator, and the probability of getting 4 males, given all of these conditions, would be 0.0433. Okay, or 4%, essentially. So if we're looking at the next part, it says the DNA testing actually revealed that all 4 femurs tested were from males. Based on this result and your answer from part B, what do you think? Do you think that males and females are equally represented in the group of 20 brontosaurs stuck in the swamp? So just based on the fact that the probability of getting that event was 4%, and that's so small, so I'm going to say no. So no, because the chance of all 4 tested to be male is not likely. So I would then conclude like there must be a higher proportion of males. Okay. All right, so I'm almost there. I'm almost to the full 4 points. So for D, it says, is it reasonable to generalize your conclusion in part C pertaining to the group of 20 brontosaurs to all of the population of brontosaurs? Now, let's go back and read the problem for a second. At an archaeological site that was at an ancient swamp, the bones from 20 brontosaurs have been unearthed. So my entire sample is from one site. So since this was not a random sample from all brontosaurs, so no, it's not reasonable. So no, this was not a random sample, from all brontosaurs, so we cannot make that generalization. And that's it. All right, so that concludes the notes over the probability section 2. Please remember that you're responsible for completing the Check My Understanding problems for the homework that's due on Monday. All right, I'll see y'all on Monday.